So first thing I'm going to do is roll this bad boy around here. So what us engineers like to do is build things. So that's what my project kind of consisted of. I don't know if everybody can see that. Feel free to stand up if you can't. That's just a 3D model of what I designed. You may not know what it is right now, but that's what we're going to get to here in a moment. So I've been working on a project that I like to call the Safe Drinking Water Initiative. This is actually going to be the continuation of a design project that I've been working with some classmates this past semester on, alongside with our advisor, Dr. Chen, who is a professional engineer in the civil engineering department here at IPFW. The first thing to identify in any engineering problem is the problem itself. So about 85% of the world lives in the driest half of the planet. This is a number contributing to almost 2.5 billion people without adequate sanitation and about 783 million people who don't have access to clean water. Living in the United States, this seems pretty foreign to us, as we usually have water at our fingertips, except for the past 48 hours here in Fort Wayne, where our plant went down for just a couple minutes and now we have to boil our water just to drink it. But again, 6 to 8 million people die annually from the consequences of water-related diseases from either one of these two cases shown here. This is just an underdeveloped country. As you can see, this little girl is getting water from a well there and putting it in water bottles to drink. Just by the color of it, you can tell that it's not sanitary at all. And there's probably a lot of parasites and bacteria that could adversely affect her health. On the right side here, we have what's actually happening here in the United States in Flint, Michigan. This is just some of the Army Reserve delivering pallet after pallet of drinking water to that city. So if we could design a system that would not only clean the water, it would maybe save some lives in the process and reduce some waste shown here. So what do civil engineers have to say about this? I want to start out by there's usually 5 main parts of civil engineering. You got construction, structural engineering, geotech, which is anything going to the soils, and then transportation. The one that this project focused under is environmental engineering, which could be anything from sustainable energy sources to cleaning up the environment, or more specifically, water treatment. This is just a typical water treatment facility on a large scale that can provide water to whole cities. And on a smaller scale, we can develop devices to filter water as well. So that was what we were going to try to do with our project in our design class. And the first thing that we wanted to make sure is that we had a low operating cost. That's because if we were to use it for either one of those two reasons before, whether it be disaster relief or within an underdeveloped country, you want to keep this cost as low as possible. Otherwise, the community will not be able to maintain it itself. Secondly, we want it to be chemical free. Not only will it keep this operating cost down, but chemicals usually produce adversely effective health concerns to your body, and you usually have to end up putting a chemical into the water to get rid of the effects of another chemical. So we just wanted to stay away from that. Again, just low maintenance in general. We don't want people to have to maintain this every single day. And then we wanted it to be potable. But basically this means is that it's drinkable and can be used for just about anything. And in the US, that must pass the EPA standards. The EPA is the Environmental Protection Agency, and they're just a government agency that sets a lot of rules and regulations on how clean the water must be before entering any distribution system. So the balancing act in this was maximizing the flow rate in the system while maintaining the quality of the water. And then we wanted our system to be portable. That's because if we were to use it in underdeveloped countries or in a disaster relief program, we wanted it to be able to fit in the back of a pickup truck so it can be transported within those remote areas. So the solution that we decided to go towards is a slow sand filter. We chose this mainly because of the advantages seen here are a lot of the ones that I just talked about. And the main disadvantage I wanted to touch on was that high turbidity water can clog the fine sand that's used in this type of filter. This is usually when the turbidity is over 10 NTU. So what turbidity is just a measure of the suspended particles within water. And these particles can then clog up the system by getting caught in between the sand. So coming out of the system, we want this number to be less than 1 NTU, which is the Environmental Protection Agency's regulations for water. So right here is a cross section of what one of these filters might look like. First, you're going to pump water into the water inlet at the top. During the design concept, you want to keep in mind that you want the height of this to be as low as possible. That way you're not wasting energy to pump the water all the way up in the system. Your first layer is the water itself. This typically ranges from about 1/3 of a meter to 2 meters, depending on the filtration rate you want through the system. If you have more water on top, then you're going to have more pressure at the bottom of that, therefore more force pushing the water through the system faster. The second layer is Schmenk, and this is actually a German word for the microorganisms that are grown in this system. These microorganisms act as actually the first cleansing part of this system. So they will actually eat the bacteria and use that as a food source that is found in the water. So the second cleaning part is the sand bed. This is typically used with engineered sand that ranges from diameters of 0.2 to 0.3 millimeters, so very small. And you want these sand particles to be as close to the same size as possible. That way, if you have larger particles and smaller particles, those smaller particles will fill the voids or empty space in between them, and that will create clogging as well. These are typically about 1 foot to 3 foot tall, depending on how much filtration you want and what your water quality you want coming out of the system. Lastly, you usually see a supporting gravel layer. This just acts as structural support for the sand before the water leaves the system that can be controlled by the valve shown down there. So this is the design that my team came up with this semester. We actually took out that gravel layer in the slow sand filter just because we didn't think it was very necessary. And we added a sedimentation tank. And what this will do is solve that turbidity problem that I mentioned earlier. So what you'll see is the water enters the tank right here that has this divider. This divider will force all the water, including the larger particles, to go to the bottom of the tank, and gravity will keep those particles down there while the water is allowed to come back up. So that already cleaner water can then enter the slow sand filter, which is where all the magic happens, as explained before, and then it goes into our storage tank over here. The height of the water and sand will be determined when we start our testing on the system, but this H value right here we could determine during our design. So what this H value is the head loss within the system. So it's basically a potential energy drop as energy is lost through the friction in the sand particles. So the faster the water goes through that system, the more energy loss that you're going to have. So the idea is to get this system as horizontal as possible. That way you're not wasting energy pumping it into the system. And we've calculated this H value to be about 2.4 inches. So because our water is going so slow through this system, it wasn't too big of an issue. The next thing to design was how big the system would have to be. So we decided to take an ideal population of about 2,000 people, which turned out to be a very fortunate number, as I'll explain here in a minute. But we decided to use tubes like shown over here. We decided to use 4 tubes in their sand filter process. That way, if one becomes defective, we still have 75% of our system working. So with 2,000 people, we just estimated 2 liters of drinking water a day would be sufficient, and that gave us a flow rate shown by Q. Dividing that flow rate by the average velocity of a slow sand filter, you can get a surface area that we might need, and we then convert these units from meters to inches because the United States doesn't go by the metric system like the rest of the world, so we have to be difficult in that portion. But I use this 5 to 7 ratio because the bed of a truck is typically about 50 inches by 70 inches. So that gave us our dimensions to fit within that. And they came out to this, so fitting 4 of those beside each other will fit within that 70-inch to 50-inch range that I explained. So next we went on to 3D modeling for the device, and that's what you're seeing down here as well as up here. All you're seeing in this part of the system is the sedimentation tank and the sand filter tank. The storage tank is not seen here because that wasn't a big design portion of it. So water will enter the system through the back of the sedimentation tank, seen in that little hole there. And I got a little video here to kind of show you how the system will end up working. So first what you're getting is a nice little 360-degree view of this beautiful system. And then that right there is the sedimentation tank. So the cool thing is that all these parts basically come apart, so they can be cleaned out. The sedimentation tank lid is what's providing that divider for that water to be pushed down within the system. And then that allows the tank to be dumped. The tank will have to be dumped probably about once a week, maybe a little bit more, a little bit less, depending on how dirty the water going into your system is. And that tank's going to be heavy if it's filled up with water. So there will be some type of release valve within the bottom of that, so that can be lifted off just by the power of man. So that's going back onto the system, onto the sand filter part here. And the water will be stored in this blue tank. And if you plug one of those holes that you're seeing up there, that'll make it so the water cannot continue on through these sand filter tubes that are shown below. These support grids right here will end up having hinges on them, allowing one of those tanks to come out of the system. This is just primarily for maintenance purposes. If the sand's really bad, it can be dumped as shown there, but most likely you just have to clean the top layer off about twice a year. So again, not a whole lot of maintenance within that. As well, if it got cracked or something, it'd be easy to replace. What you're seeing now is the transportability side. As you can see, those support grids fold nicely up under the water tank to begin with. And then these filter tubes are designed to also fit the poles that are used for support within that. So all this material will be made of lightweight material, most likely heavy plastics or wood for the case of the support beams. So those will fit nicely within that tank, and then the sedimentation tank is designed to come off as well and strap onto the top of that, and this whole system would then fit in the back of a pickup truck, which was one of our main design goals for this. So where to put this system specifically? We actually pinpointed a village in Africa for this system to be used. It's the village of Sandaba, which is in Burkina Faso, Africa, which is shown by that pinpoint on that map. This is a very underdeveloped country. When you think of Africa and the stereotypical kids having problems with food and water, this is it. So it's got a population of about 2,000 people, which is perfect. That's the amount that we had designed for. And it's also even more perfect that Engineers Without Borders at IPFW just submitted a proposal to solve their water problems there. Now their project, they're focusing primarily on water for agricultural purposes. So they're going to create a reservoir that's large enough to supply them with water for their crops during their dry season. So Burkina Faso goes through about a 6 to 8 month dry season where they see almost no rain. So pairing this sand filter with that reservoir that they will be creating, we thought it would be a good thing to add to their system. And they were really excited to see this design and are interested in scaling up their reservoir to meet the water rate for this filter. So they're looking at an assessment trip in the late fall and early spring that I hope to maybe tag along with. Not only will we be able to see how our systems can work within this community, but we will also be able to find some African suppliers of materials. And this is important because Engineers Without Borders actually requires this to be built within the country. That way, if something gets broken, that it can be replaced with the resources that they have there. Kingdom Investments International is the non-for-profit that is working alongside with Engineers Without Borders. And I actually just had a Skype interview with them yesterday, and they really liked the idea of the system, and they believed it had plenty of use for the work that they do in Burkina Faso. They actually even expressed interest in teaming up outside of the Engineers Without Borders project and bringing on smaller filters to be used within their hospitals there that would not only supply drinking water, but clean water to clean wounds and other stuff like that. This was some of the pictures that John Paul, who's the president of Kingdom Investments, sent to me yesterday. So this is just some of the rural parts of Sandaba. As you can see, their houses are more like huts, so not very good living conditions. This is just, again, another picture of the village. What you see here, he took this picture just because this is actually a puddle that they might drink from during the dry season. Obviously, not the safest conditions that you can think of. So he thought that this was significant just because he said it's very typical for them to take their hand and scoop some water for a drink out of that. This is in a different village where they actually created a deep well. So this water is cleaner than surface water, obviously, but it's still not going to be as clean as the water coming out of our system. The one problem about this is that it takes a lot of money to dig and build a system like this. And also, as you can tell, it's not portable. So we're trying to bring that cost down and that effect to be able to touch a lot of more communities with our design. This right here is a man-dug hole that is typical for them also to get water out of. And again, a lot of places where that can get contaminated. And then lastly, this is just a little pump coming from one of those holes. Again, the children drink from that, clean themselves from that, and there's really nothing there catching the leftover water. And you can see some pigs swimming in the puddles down there. And I'd like to think that they're not going to drink that eventually, but with the way that John Paul showed us that picture of the puddle, you can never be too sure. So currently, I'm working on starting a new student organization that I like to call the World Advancement Project. I think what I have a vision for this organization is to take engineering designs and bring them to fruition. So each year, there's a lot of great engineering designs that come through the senior design class at IPFW, but these designs never get to be constructed. And so I think it'd be cool to get underclassmen involved in these designs and seeing them and actually bringing them to fruition. This has already been approved by the Student Senate, so now all I have to do is find enough members to be considered a student org. And then we're also submitting grants for supplies and a possible assessment trip funds as well. Just got done ordering sand. We actually got it donated from Red Flint out of Wisconsin. So that gives us all the supplies that we need for our model, which we'll be working on this summer. This is what our model will look like. The sand will be put into this first tube and water will be put in that second tube and placed on top of that. So once we find out the minimum amount of sand to get the water quality we want coming out of these tubes, we'll have our measurements that way, as well as the water velocity coming through the system. We'll then recalculate everything to be specific to our system, and then we'll do several months of water testing just to make sure that the system withholds after 7 months is still giving us the same quality out of the system. Once we know what that is, we'll determine the final materials for the larger project that you see here as a model, and we'll reach out to local companies for donated supplies, and hopefully some sponsorships would be nice. In the fall, we'll start student organization activities, as well as start construction on the sedimentation tank, slow sand filter, which is shown up here, as well as the storage tank. So the idea is to build it here and get an idea of how everything goes together, and then possibly take that assessment trip with Engineers Without Borders. After we take that assessment trip, we'll be able to determine the African suppliers of materials, and then I'll start creating manuals. And 2 manuals that are required by Engineers Without Borders USA is the installation manual and the maintenance manual for the system. Also, we'll use the Fort Wayne built system to teach and implement how to use this system here in Fort Wayne. They won't be able to get to their reservoir project probably until 2019, 2020. And until we have that source of water, we won't be able to use this in there. So after talking to them, they really like to bring this project on as their own after I leave. So once I create those manuals and have that system made here for them to learn how to use it, everything will be set for them to then take this to Africa, this idea, and make it work. And then lastly, we'll find future use for that Fort Wayne built system, whether that be displaying it on campus, donating it to the Red Cross or Flint, Michigan, or any other place that might need it. So I'd like to take this last little bit for some acknowledgments. First off, Dr. Chen, who's sitting in the back there. He's been a tremendous help on both sides of the project. He's a wizard when it comes to this stuff, so he's really good with that. My senior design team, which is shown up here, and then also Glenn Crawford is another name that I'd like to mention, who is going to be joining our testing team this summer. Engineers Without Borders, specifically Dr. Thompson, who's their advisor, and Cy Bentley, who's their president. They've answered every question that I've had about their project and how they can fit together. And then Kingdom Investments and their president, John Paul, as well as Red Flint Sand and Gravel for donating our materials. And I'd also like to thank Kelsey and Craig and Kim for helping us out with this project and whether it's proofreading our abstracts or just getting us prepared for this presentation. You guys have been a tremendous help for that as well. And with that, I'll leave it open to questions. So thank you.
Okay, maybe it's a technical question, but I imagine in your original reference design that you looked at, you had that gravel layer on the bottom. Mm-hmm. And so my first thought was that maybe that would keep you from losing your sand through your output valve. How do you prevent from doing that with your filter?
So, this way. So, as you see here, this system has actually been tested before on sand, and they got a layer of like a mesh that won't allow the sand particles in, but just water. So that will keep the sand from exiting the system.
That is a great idea. I think it's awesome. My one question is, how much does one of those machines cost to make?
So this machine right here is our original design. Usually sand filters are made out of concrete, and they're not really transportable as shown here. So we haven't gotten to that part yet because we're not sure what materials we're going to need for the system. A lot of this last semester has been learning more about slow sand filters and coming up with a design as far as filtration rate and how big we're going to need to make the system. So once we figure out all those through the testing, we'll be able to find what supplies will withstand the heat in Africa and be able to use there that's as cheap as possible.
I don't have really a question, but a comment, because I just shipped a ton of stuff to Africa for our marketing research last month, and their like shipping standards are really weird in Africa. So I guess like my tip to you before you like settle on all the materials that you're going to use, or maybe just check and make sure that they're all good to go as far as entering the country before you like decide on a model and then go to ship it there and they're like, yeah, we don't take that kind of sand.
Yeah. So the actual thing will be built with all the materials in Africa. So that's where Kingdom Investments is going to be huge in this. They do a lot of work in Burkina Faso, specifically just Burkina Faso, and so once this gets closer to the actual implementation stage, they'll be looking for suppliers within Africa for us on their trips and setting those relationships up for us.
I know a lot of this probably depends on the materials that you end up using, but what's the expected lifespan of a device like that?
A device like this, I mean, as long as it's maintained, I mean, the sand's really the only thing that's going to see a lot of wear and tear. Possibly the support poles just from holding up that much weight once you get the water and the sand within the system. But I've been looking at plexiglass and other hard plastics that are resistant to heat that will be experienced in Africa, and if we can get those that won't warp over the temperature, then those should last for a fairly long time, years.
So these could be a long-term solution for a community somewhere, as well as disaster relief?
Yes, as long as it's maintained and nothing crazy happens like an earthquake that drops it down in the middle of the earth, it should be maintainable. Yeah.
Do you see a project being applicable to other countries or to other villages? So.
Yeah, of course. That was kind of our design, just for it to be used just about anywhere in the world. The one reason why we're not keeping it too easy to use here in the U.S. is just because of the EPA and their high standards. If somebody were to get sick for some reason, that's a lot of liability that we didn't want to really deal with, obviously. So when I heard that Engineers Without Borders is actually already working on this project in Africa, I saw it as a perfect opportunity to tag along with them.
Do you have any plans to patent your design?
No, not really. But I suppose that could be something to keep in mind moving forward once we know what materials we're going to use and have a bill of materials and everything to go towards that. And if it still seems like a really great idea, that'd be something I'd look into, definitely. Gigi?
You said one of the main things you wanted was that it could fit into the back of a pickup truck. How often do you expect it to be transported around?
I mean, that just depends on the situation. Obviously, if you're putting it in a village like this, it wouldn't be a whole lot. But if you're using it for disaster relief efforts, and if a organization like the Red Cross or any organization like that has ownership of it, they can ship it to wherever that may be whenever that disaster hits. Sheree?
So for the installation and maintenance manuals, have you guys considered like language barriers, or is that not really an issue?
Yes, that's actually an issue that Craig pointed out to me a week ago. And so in this area, French is their main speaking language. So that would definitely be the first thing. I think Kingdom Investments can help us out with that a lot because they have, their office is out of Bellefontaine, Ohio, so it's fairly close to be working with them for translation, as well as they have plenty of people who are full-time workers within Burkina Faso itself. So I think we would be able to use Kingdom Investments to kind of translate that with the language barriers there. Brian?
So like you see like a lot of things on the news of like people with those cool like little straws and they're going with like a dirty little stream like that right there, and they're getting like clean water and like that, and there's like plenty of other systems like that. So I think my question is like what kind of sets your design apart from the like plethora of other designs used to filter dirty water?
Yeah, so first off, I mean, personally, I wouldn't want to have to carry a straw with me everywhere I go just to get a clean drink of water. But something like this, just that it differs from regular sand filters. Sand filters are used quite expansively in countries like this, but are designed just that it's easily to come apart in case something gets broken within it. Hopefully it'll be made of less expensive materials as well, and the fact that it's transportable as well, that everything kind of comes apart and can fold up into a small design. That's how we believe that ours differs from the others. Logan?
How are you going to pump the water into the sedimentation tank?
Yeah, so we'll either use a hand pump that will be used by them, or a solar power pump. Those are the big ones that Kingdom Investments already uses in some of their systems that they have. So just, I'm not a mechanical engineer, that's more on that side of designing that pump, but from my understanding there's already similar ones like that designed that we'd be able to use. And that would probably be the biggest expense coming from the system.
The reason I ask, when I went to Cuba, there's a guy from Franklin Electric who was going, Franklin Electric's actually creating something. I don't know if they use a sand filter, but they're actually creating pumps for your water. So I don't know if that's something that you could talk to them about. Maybe you could get some free pumps out of it. I don't know exactly. Yeah, well, but it's a resource you can use.
Abby?
So for your system to work, obviously you need water, and you mentioned a dry season. How like realistically applicable could this be to other countries that wouldn't have, maybe like you were talking about, they're building that resource, the reservoir of water for this particular town? How applicable would that be to towns that don't have that type of, would they have to go hand in hand, I guess is my question? Yeah, I mean, yeah, you're gonna have to have some type of water source, whether that be a river, a lake, a well, something. This system needs water to run, obviously, and to clean. And so wherever that source of water may be, that's where the system like this could be used. So that's possibly a limitation to your ability. Yeah, of course. Kingdom Investments actually, after talking to them yesterday, they wanted to invite me on a trip just by myself in November to maybe build some of these within some of their hospitals that they have there. But again, they said that there's a huge limitation on just water in general for the reasons of the dry season in this part. So that's why I think teaming up with Engineers Without Borders is a much more feasible idea because they'll create that water source for us to use. Scott?
You mentioned that you would be using engineered sand for its qualities of being more fine and better able to filter. Would there be a concern of eventually running out of that sand and not being able to replenish it in the filter?
There is filtration sand that's engineered in Africa, so I've already looked into that.
Follow up to his question, is there anything, or have you considered in your design, error-proofing your filter itself so that they couldn't use the non-engineered sand or something inappropriate sand to replace it? So in other words, when the community regenerates the sand, to keep them from putting something that's
yeah. So yeah, Kingdom Investments, they actually have a maintenance agreement with whatever village that they end up working with. So that would be something that they'd be able to put in that maintenance agreement to make sure that they're putting the right sand in there. If you don't put the right sand in there, I mean, the system will still work technically. It'll just get clogged a lot faster and you'll have to clean it out even more. So that's how it might ruin the system. But again, with that maintenance agreement that they set up with the heads of the villages before installing something like this, hopefully in those agreements we'd be able to establish that they do go to the extent to get engineered sand, so it's more efficient.
Can the sand be cleaned, like when it clogs and becomes overly contaminated? Do they have to just get rid of it and put new sand in, or can they take it out and clean it and then put the same sand back in?
Yeah, so I mean, sand can obviously always be cleaned. In fast sand filters, you get a lot more flow rate coming through the system, but the quality of the water coming out isn't quite as clean. So in systems like that, usually they have a backwashing where they'll take the water and pressurize it back through the system and pushing those particles then back. I mean, if you think of a water filter at home, if you put the water the other way, you know, I mean, it's going to push out the other side out of those particles. So that's usually in rapid sand where your particles are much bigger. So I assume that you'd be able to take out that top sand and do some type of system like that where you're able to get the particles and separate them and clean that sand to be reused, yeah. Which is another cool thing that I like, that it has 4 of those separate tubes, because if you were to do something like that, then it can still work at a 75% capacity, which is pretty neat.
Could the design be adjusted to fit a specific need? Like if, I don't know, could you add more or fewer filter compartments?
Yeah. Of course, I mean, you just have to yeah, use the different sizes, different quantities that you want to fit. If you want it to be smaller and just be used for a couple households, you could definitely scale down the system for that as well. I mean, basically, the science behind it, I mean, we're going to be testing something like this, so, I mean, it could be 1,000 of these put together, just depending on how much water you wanted to filter, so.
Yeah. You realize your own mother claims she doesn't have clean drinking water. Why don't you scale that down, make a residential one out of there, and then go to Shark Tank or something?
No, I don't know about you guys, but I like our water at home. I mean, that well water's, it tastes pretty good, so I'll keep that as is. So that's my parents, everybody. So no.
You've mentioned starting a club, a student club, to actually maintain this, which I think is a really good idea. I mean, I've probably seen all of the Chapman projects at some point, either as proposals or as in their final showcase presentation. My question, I guess, with regard to this, do you see the club, I mean, it will be hopefully surviving you, do you see it maintaining just this and broadening where it's actually going to be implemented, or actually taking additional senior projects that would come down the line and actually implementing them? And how would you, I mean, that has the potential now for actually having several projects being presented and maintained. What do you foresee for this club going forward?
So yeah, for the club, obviously the first year I would like to focus on this project since we've already gotten started on it. And so it would basically be building that Fort Wayne system here, as well as creating those manuals to hand over to Engineers Without Borders. At that point, it'll be part of their proposal through Engineers Without Borders International, and it'll get implemented within the village, hopefully, if everything gets approved through them. And then it'll be there to be maintained within the maintenance agreement that Kingdom Investments makes with the village. So as far as maintaining the system while it's there, that will be out of our hands. And then yeah, the idea for this, for future years, is to take different projects. One project that's going on right now in the design class that I'm in, that I'm not part of, is a rain garden on IPFW's campus. That's basically to help clean off some of the runoff water from the pesticides and from the lawn runoff and whatnot like that. And before it enters the rivers again, this garden would not only serve as looking good on campus, but it would clean the water before it goes back into the rivers. That's a design that they came up with, and they've been working on it to be used within our campus. They've even looked at certain spots that would be the best place to put it, and they already have that design set up. So having a organization that could take that idea, since a lot of those are seniors who are graduating and moving on, to take that idea and implement it, that would be the ideal situation to keep this club going.
So more individual projects each year, not maintaining those that have come before.
Correct. Thank you.